My name is Chris Ray. I work with Energy to Power Solutions, and the title of my talk is Spatially Integrating Magnetometer. The topic number is N192-122. Before I jump right into the technical aspect of this talk, I'd like to give you a brief description of our company. E2P is a high-tech firm specializing in both low-temperature and high-temperature superconducting devices, such as magnets, motors, power cables, and degaussing cables, and their associated cryogenic, high-voltage, and magnetic measurement equipment. In our company history, we've had over 30 Phase 1 SBIR STTRs, 7 Phase 2s, and 3 Phase 3s. We have 7 patents. In terms of commercialization, we've commercialized HTS degaussing systems, which are currently being installed by Huntington Ingalls on LPD 28 through 31. We currently have a Phase 3, DARPA Phase 3, dealing with the expendable, low-cost, compact magnetic minesweeping. Our device was recently tested at a sea trial on a Trident Spectre this past July 22. And for non-Navy commercialization, we have commercialized various components. One went on the NASA Astro 8 satellite. We also work with Commonwealth Fusion on supplying components to them, General Atomics and supplying HES magnets, Lockheed Martin, etc. Key resources: our HES magnet and cable fabrication facility, and our only source of E2P is the only source of cryogenically rated voltage bushings greater than 10 kV. Our facilities are located in Tallahassee, Florida. We have over 2,000 square feet of lab space. We have cryogenic test capability down to 3 Kelvin and high voltage test capability up to 160 kV DC. What is the Navy challenge or interest? The challenge is to improve the performance of closed-loop degaussing systems currently used by submarines by rejecting the unwanted influence of localized magnetic perturbations, such as welds, electrical equipment, etc. These local magnetic anomalies skew the existing discrete flex-gate magnetometer sensors, resulting in incorrect CLDG output, and thereby possibly leaving the vessel vulnerable to magnetic detection. What is the GAP/science and technology objective? Well, we want to synergistically combine 3 independent spatially integrating measurements. The first is a spatially integrating optical magnetometer. The second is a scanning flex-gate magnetometer. And the third is a scanning integrated gradiometer to measure the integrated B.dl and integrated G.dl measurements. What is the benefit? E2P's measurement system uses a single scanning flex-gate magnetometer versus the 40-plus discrete sensors currently used in Navy technology. Next, we discuss the operational use and improvement of the flex-gate magnetometer. The question we ask ourselves is how many existing discrete flex-gate magnetometer sensors mounted on a ship's hull does it take to get an accurate measurement of the integrated magnetic field, B.dl, when a localized magnetic perturbation is present? The answer is surprising. It takes over 100 flex-gate magnetometer sensors to get the correct answer. Note that this is dramatically different than the actual number of sensors mounted on a submarine's hull. The actual number of sensors is closer to 40 to 60, indicating that the 40 to 60 may not be giving us the most accurate measurement. To illustrate this, we perform a sample problem. In our sample problem, we initially start off with no magnetic perturbation, denoted by M sub P equal to 0. We place 3 sensors, flex-gate sensors, on the periphery of a submarine's hull. We place one located at the 0 degree position, one located at the 120 degree position, and one at the 240 degree position. We then energize the CLDG coils. When we energize the CLDG coils and we take measurements of those 3 sensors producing a uniform field, we have assigned that value, that uniform field value, as one arbitrary unit of magnetic field. We next place our magnetic perturbation on the periphery of the hull. We place the magnetic perturbation at the 120 degree location. We assign it an arbitrary value MP equal to 9 arbitrary units of magnetic field. Then when we take the exact same measurement that we did previously with no magnetic perturbation present, and we measure the same 3 sensors located at the 0, 120, and 240 degree positions, we find that we get a measurement value, an average value of magnetic field from those 3 sensors of a value of 4 arbitrary units. In other words, that single magnetic perturbation has dramatically altered the integrated magnetic field around the periphery of the hull. It has changed it by a factor of 4, a dramatic difference from its original value of 1. The question we ask ourselves, what is the actual correct value? We know it is no longer 1 because we've added a magnetic perturbation, but it is certainly not a value of 4, as that is too high because of the location of the perturbation happens to be in close proximity to one of the sensors. It has skewed the integrated value, or the average spatially integrated value, around the periphery of the hull. The easy answer may be, let's add more sensors. So suppose we go to 5 sensors. Again, the same magnetic perturbation of MP equals 9 arbitrary units located at the 120 degree position. We now have 5 sensors evenly dispersed throughout the periphery of the hull. When we take this measurement, we get an average value of 1.08. Do we know if that is the correct value? The only way to know what is the correct value is to add an infinite number of sensors. When we add an infinite number of sensors, if you look at the graph on the right where we have the average field value reading as a function of the number of sensors, we find that it takes close to 100 FlexGate magnetometer sensors to asymptote into the correct value being closer to 1.2. So in our sample problem, neither the 3 sensors nor adding more sensors gave us the accurate number. In fact, what we find is it takes nearly 100 sensors to get the correct value. This shows the power of a single scanning FlexGate magnetometer. What is our proposed solution? Our proposed solution is to use a single package that has 3 independent measurements to measure the integrated magnetic field and integrated gradient along the periphery of the hull. The first independent measurement system is an optical magnetometer. This is a true direct integral measurement of the magnetic field. This is the only type of device of its kind in the world. The second is to translate a gradiometer or scan a single gradiometer along the surface of the measurement. This allows us to calculate the integrated gradient around the periphery of the hull. And the third independent measurement is to translate a single FlexGate magnetometer along the axis and then to calculate the integrated B field value. Both the optical magnetometer and the scanning or translated FlexGate magnetometer provide the same answer, which we can independently verify with one another. What is the current status of the project? As of February 2023, there are approximately 3 months left in this project. We have completed 100% of task 1, 100% of task 2, 100% of task 3. We are approximately 90% complete on task 4 and 90% complete on task 5. Next, we discuss the current status and what are the program risks. In terms of schedule, there are no schedule issues. A no-cost extension was granted in early 2022, and the program expires in May of 2023. In terms of cost, there are no cost issues. In terms of technical risk, we do not foresee any technical risks. All 3 independent measurement systems are working properly and providing accurate results. The single biggest issue that we have in terms of risk is in terms of transition. The technology outside of the program. We have continually requested an opportunity to speak to various stakeholders interested in this technology, interested in the spatially integrating magnetic magnetometer technology, and we have not been able to do so to date. If the phase 2 option 1 is granted, we are currently supposed to work with Ultra EMS, the fabricators, one of the Navy's fabricators for CLDG systems. They have expressed an interest, but unless the phase 2 option 1 is exercised, this technology will die on the vine and will not transition. So once again, we are requesting an opportunity to speak to the various stakeholders in the Navy interested in technology. Next, we discuss the key features, advantages, and benefits of the technology. The first independent measurement system uses a fiber-Stokes polarimeter integrating optical magnetometer. This measures the Faraday rotation, or the change in angle of polarized light when subjected to a magnetic field, where the change in that angle is given by the Verde coefficient, the magnitude of the magnetic field, and the optical path length. The second independent measurement uses a scanning fluxgate magnetometer. The scanning fluxgate magnetometer uses a single fluxgate magnetometer mounted on a flexible scanning platform. Longitudinal scans are then performed to calculate the integrated magnetic field and integrated gradient along that path length. The third independent measurement system uses scanning integrated gradiometer. A gradiometer, which uses two fluxgate magnetometers, is mounted on a flexible scanning platform, and once again, longitudinal scans provide the calculated value of the integrated B field and gradient. The scanning fluxgate and the scanning gradiometer scans are only performed when the ship does not have to be stealthy, such as its initial construction, when it's at shore, or sea trials. These scans are never performed when the ship has to operate in its stealthy mode. So in those cases, the fluxgates and the gradiometers are in a fixed position. Once again, these scans are never performed when the ship has to operate stealthy and are only performed when the ship does not have to be in stealthy mode, such as its original construction or when it is at shore. The benefit is a single measurement package reduces the upfront capital cost, the OEM cost, the installation complexity, and improve efficacy over existing use of multiple discrete fluxgate sensors. The current project is at a TRL level 4, and by the time it's projected to finish this coming May of 2023, we will be at a TRL 6. Next, we show some initial data. In this case, this is our benchmarking phase in which we measure the air core of what we call configuration A. The air core configuration has no magnetic shield or no magnetic hull present and no magnetic perturbations. So in the benchmarking test apparatus, what the purpose is to compare the calculated value versus the experimental value. Step 1 is we calculate the magnetic field using finite element methods in both the attractive and repulsive mode. That is when the CLDG coils are either energized in the same direction or in opposite directions. Next, we measure the magnetic field along the axis with the CLG coils in both the attractive mode and then in the repulsive mode. Then, finally, we compare the calculated value from step 1 and the measured value in step 2 to the longitudinal, the azimuthal, and the vertical magnetic field values. We found that during our benchmarking phase, they were in excellent agreement, giving us high confidence that our measurement technique is valid. Our second benchmarking exercise is one in which we introduce a semi-uniform steel hull. We call this configuration B. Similar to its previous one, the air core configuration, we now slide a steel hull and perform the same 3 measurements that we did before. Keep in mind that no magnetic perturbation is present. In this case, we measure the integrated magnetic field using both our scanning fluxgate magnetometer and also our fiber-Stokes polarimeter, integrated optical magnetometer, and compared the two measurements. Once again, we found under simulated conditions, both the scanning flex-gate magnetometer and the integrated optical magnetometer give similar results, once again giving us high confidence in our measurements. Next, we discussed the transition to the fleet. As we explained earlier, a primary issue we were having is regarding commercialization is access to contacts within the Navy transition sponsor and introduction to shipbuilders that install/implement existing CLD technology. To date, despite multiple requests, we have still not been able to make those contacts. Is there any potential for Phase 3 funding? E2P has been in ongoing discussions with Ultra EMS of Yaphank, New York, who currently provides existing CLDG systems to the Navy regarding the transition of the spatially integrated optical magnetometer into future CLD systems. Ultra EMS has agreed to be a subcontractor in the Phase 2 Option 1 if it is funded to help the transition of this technology. However, minimal assistance in the Phase 2 base effort, the one we're currently in, has been given. We will need the Phase 2 Option 1 to have any traction via this limited approach. What help can you give us? Identify a primary advocate and allow E2P to directly communicate with the Navy transition sponsor and potential user platform. And in addition, we are requesting more frequent communication with technical personnel to better understand technical issues regarding what is practical and what is not practical for our approach. So what is our transition partnership pitch? Step 1 is we want to set up a detailed technical review of the technology with the Navy transition sponsor. Step 2 is to fund the Phase 2 Option 1 and 2, which automatically triggers the participation of Ultra EMS, who is a prime contractor for existing CLDG systems for the Navy. Step 3, team with the prime, such as Ultra EMS, and set up a sea trial evaluation, such as Trident, Spectre, or PACRIM, to evaluate the technology. And finally, sell subsystems to a prime for integration on future submarine platforms. In summary, existing closed-loop degaussing systems use greater than 40 discrete flex-gate magnetometer sensors along the periphery of a submarine hull to measure the integrated magnetic field and gradient of Virginia-class and future Columbia-class submarines. Unfortunately, localized magnetic perturbations from welds or electronics, motors, etc., can often skew existing discrete FGM sensors, resulting in erroneous B.DL and G.DL measurements, and hence provide poor CLDG output in making the submarine vulnerable to detection. A sample problem that we performed shows that a single localized magnetic perturbation would require greater than 100 FGM sensors to obtain an accurate B.DL and G.DL value. Note that in our sample problem, more than 100 sensors are required, which is dramatically larger than the actual number of sensors installed on a Virginia and future Columbia-class submarines. Spatially integrating systems average out localized magnetic anomalies, but still correctly account for their magnetic contribution. E2P's proprietary system provides 3 independent spatially integrated measurements using a spatially integrated optical magnetometer, a scanning flex-gate magnetometer, and a scanning integrated gradiometer. Initial benchmark measurements tests performed on 2 configurations, both an air core solenoid and a semi-uniform permeable shell solenoid, were consistent with FEM calculations, giving us high confidence that our 3 independent measurement systems are providing the correct answers. All 3 B-field measurement systems provided repeatable, consistent, and accurate B.DL and G.DL measurements. E2P's integrated measurements are lighter, more compact, have a lower upfront capital cost, lower long-term OEM cost than existing multiple discrete technologies. E2P's contact information is provided below. Thank you very much.